If you build a highly complex structure without internal firewalls, a single microscopic flaw will shatter the entire system. In modern distributed environments, we build out of microservices. Your application relies on external dependencies, other services, databases, message brokers like Kafka. By definition, every single one of these network hops is a point of failure. Compounding this risk is a strict rule in highly scaled systems. Cross-entity database transactions are entirely forbidden. You cannot wrap multiple service updates into a single, safe transaction block. Any write operation after the very first one is vulnerable to failure. This diagram models a standard synchronous e-commerce architecture. We have a central checkout service handling a user's order. To complete the transaction, it makes synchronous calls to a local database, a coupon service, and a paid plan service. Now, observe what happens when a non-critical downstream dependency fails. The coupon service experiences a sudden CPU spike and drops offline. Because the connection is synchronous, the checkout service waits for a response that never arrives. The failure propagates backwards, consuming the caller's resources and taking down the primary checkout process entirely. A minor coupon glitch destroys revenue. Attempting to build a system where hardware and networks never fail is a mathematical impossibility. The hardware will fail. The network will partition. We engineer for resilience by assuming failure as a default state. The objective is strict architectural isolation, designing boundaries that contain local faults before they trigger a system-wide cascade. To sever these failure chains, we have to audit the specific network calls triggered by the core service. Every external dependency must be rigidly classified as either critical or non-critical. If a critical dependency drops, the service must fail gracefully and log the error. But non-critical dependencies require a different protocol. On our architecture graph, we design for degraded service. If the coupon system breaks, a fallback path routes the transaction directly to standard payments. We control these routes using feature toggles. Automated scripts flip the switch, activating the fallback and shielding the core system. We can minimize the blast radius even further by limiting invocation. The code must be conditionally structured so it only reaches out to the paid plan service if the product actually carries a paid plan flag. We do not send unnecessary traffic across the network. To handle a fragile dependency, remove it from the critical path using data materialization. By utilizing localized key-value caching inside the checkout service, we maintain a local copy of paid plans data. The network call is eliminated, ensuring uninterrupted operation if the primary source fails. By classifying our calls, deploying feature toggles, and caching data locally, we physically remove fragile network links from our critical path. When a sequence of operations halts abruptly in the middle of execution, it leaves the environment in an unresolved, highly dangerous state. Because we operate without distributed transactions, any multi-step database write carries severe risk. The first write might succeed, while the subsequent network calls fail. In this sequence diagram, the checkout service successfully writes an order to its database in step 1. In step 2, a synchronous RPC to update inventory fails. The system is fractured. Local database says sold, but inventory says available. This is a severe state corruption. You must never use synchronous RPC calls for side effects. To maintain consistency, we offload all subsequent writes to an asynchronous message broker, like Kafka or an async task queue. But putting messages in a queue does not solve the delay between the first write and the final update. To protect the system's state during that window, we implement the zombie pattern. In this new sequence, step 1 creates a database entry in a hidden pending state. It's a zombie, invisible to downstream logic. The service fires requests into Kafka for inventory and payments. When these asynchronous tasks complete successfully, the entity flips from pending to active. When structuring these Kafka handlers, avoid grouping distinct writes together. If a handler updates inventory successfully but fails on payments, the entire handler will retry, repeating the successful inventory write. You must split them into independent, isolated tasks. Furthermore, Kafka guarantees at least once delivery, meaning duplicate messages will inevitably occur. Your handlers must be idempotent, utilizing execution guards to ensure a duplicate message does not result in a duplicate charge to the user. By forcing states into a holding pattern until asynchronous tasks confirm success, the zombie pattern ensures that partial failures never translate into permanent data corruption. Isolating state prevents data corruption, but a resilient architecture must also defend its local infrastructure capacity from network latency. This bar chart models a server's connection pool. When an external service struggles, the local service keeps connections open, waiting for a response. Pending connections rapidly accumulate. Once the pool hits maximum capacity, it is exhausted. The paralyzed local service cannot process new user requests. Standard high, static timeouts leave connections hanging open far too long. We replace these with dynamic request deadlines. A deadline activates exactly when the caller's threshold is crossed, ruthlessly severing open connections and instantly returning the pool to a healthy state. Once a deadline terminates a connection, blindly retrying the request will only hammer a downstream service that is already failing under load. Retries must be strictly conditional. We only retry if the error codes confirm the failure is transient, and we execute those retries using exponential backoff to pace the network traffic. We apply this resource division to our storage layer. To protect the primary master database, we split connection pools into distinct read-only and read-write channels. If a heavy write locks the master, the isolated read-only pool cleanly bypasses the congestion, routing directly to local replicas. A resilient service prioritizes its own survival. By enforcing strict deadlines and splitting connection pools, a distant network bottleneck cannot drain our local capacity. Scaling these local defenses up to a global level requires precise traffic orchestration. When engineering services that process massive volumes of public user traffic, local resource limits and architectural boundaries are no longer enough. We have to map our topology across physical geography. Critical services and every dependency they rely on must be deployed redundantly across multiple physical data centers. Within this multi-data center topology, cross-data center communication is strictly prohibited. A service in data center A cannot call a dependency in data center B. Total encapsulation is required so that if a region fails, it fails cleanly. Before a system like this handles a single live transaction, engineering teams conduct exhaustive premortems. They map out the exact failure states, define the specific monitors, and program the automated recovery procedures. Let's view this macro architecture in action. We have DCA and DCB operating in parallel. A continuous automated health test constantly pings the critical infrastructure dependencies inside each center. Traffic is balanced. A local Elasticsearch index or primary database goes offline inside DCA. Because that dependency was explicitly mapped during the premortem, the local health test fails instantly. The failed health test triggers the automated recovery protocol. The network stops routing public traffic to DCA. Every incoming request is instantly diverted to the healthy encapsulated environment of DCB. We do not prevent failures, we contain them. By designing individual components to fail safely at a local level, we provide the global system with the precise signals it needs to reroute, adapt, and survive.